Hello, my dear student. Welcome to another edition of your mathematics lesson. Today, in continuation with your main topic, that is sequence in the series. What we are going to learn today is a sum to infinity of a GP. So let's begin. After completing the very lesson today, my dear student, will be able to find or calculate the sum to infinity of a GP. This is what I hope you'll be able to do after completing the very lesson today. As usual, my dear student, we have a favorite segment of the lesson, Mercy's Fun. Today, I'm happy to give you a relationship between the twin prime numbers and this very number 8. We are going to see this what are twin prime numbers and the relationship between the twin prime numbers and this very number 8 after completing my lesson today, so don't go away. My dear student, to begin the lesson, let me explain what is sum to infinity of a GP. This simply refers to sum of that GP that has a very large number of terms. In fact, we don't know how many terms are there in that very GP. I want to find the sum of all those terms. So sum of all those terms is what we call or what we refer here as sum to infinity. Sum to infinity of a GP is simply given by the formula. This is the formula S infinity. Look at the infinity is a subscript. So if the terms are very many, I'd want to find from term number 1 up to that last term. And we don't know how many terms are there. They are too large. So this formula is what we're going to use. So S infinity equals to A over 1 minus R. That is A, the very first term, divided by 1 minus R, where A is the very first term of the GP and R is the common ratio. This is what we now substitute A and R only to find the sum to infinity of that very GP. We are going to make use of this very formula and find the sum to infinity of a GP. So let's just move. Example number 1, we asked to find the sum to infinity of this GP. These are just a few terms of the GP. I have 1 as the very first term, 1 over 3 as the second term, 1 over 9 third term. It continues like that without ending. The terms are too many. It continues like that. We don't know the last term. And we asked to find the sum to infinity of this. Solution to this very problem, what we do first is to write down the formula. Sum to infinity, S infinity equals to A over 1 minus R. So there we determine your A, your R. From this GP, A is the first term. Look at it, it is now 1. So you now have 1, A as 1. And the common ratio, we now take second term divided by first term. 1 over 3 divided by 1 simply gives you 1 over 3. So R is 1 over 3. So I'll now substitute in this very formula. So substituting correctly, you now have 1 over 1 minus 1 over 3. Subtracting 1 over 3 from 1 gives a result 2 over 3. And this one I have here divided by this. So instead of this division, I now change it to this division symbol instead over. I now have the division sign. So 1 divided by 2 over 3. 2 over 3 is the result of subtracting this 1 over 3 from this one. So I'll continue. Division by fraction, remember we always change it to multiplication by the reciprocal. So I'm going to have 1 multiplied by, instead of this division, I now have multiplication. But the reciprocal of 2 over 3, which will now be 3 over 2. So 1 times 3 over 2 simply gives a result 3 over 2, and 3 over 2 in mixed fraction gives you one whole number, 1 over 2. This is the sum to infinity of this very GP. If you are to add this, the terms from the first to the last term, and that last term, we don't know how many before we reach the last term. The term number of terms are too many. So if we add them all together, this is what you now have one whole number, 1 over 2. So let's take another example. Example number 2, it says find the sum represented by the series. This is the series starting with the very first term 64, the next term 32, the next 16, and the next like that. So we don't know how many terms are there in this very series. And the question, remember, I didn't say some of the very first 3 or some of the very first 10 terms. No, it says sum represented by this series, as this series has no end term. So we now consider it to be summed to infinity. Solution to this very problem. We now write the formula sum to infinity, as this series has no end. So I have sum to infinity equals to 1 over 1 minus r. So I'll now find what is my A, what is my R from this series. A is the very first term, which is 64. Look at it. Next is R. R would now be second term divided by first term. So you have 32 divided by 64. And this reduced to simpler form gives answer 1 over 2 as your R. So there I now substitute in this very formula. So sum to infinity would now be equals to 64. That is your A divided by 1 minus r. R is now 1 over 2. So divided by 1 minus 1 over 2. Subtracting 1 over 2 from 1 gives a result to 1 over 2. So you have 64 all over 1 over 2. This division change it to multiplication now gives you 64 times to 2 over 1. Multiplying the 64 by 2, divide the result by 1 gives a result 128. So 128 will now be the sum of all the terms starting from the very first one up to whatever term that you have there as the last term. So this is the sum to infinity. Let's just take one more example. Example number 3. It says a GP has a first term 81 and the sum to infinity of that very GP is 729 all over 8. The question asks is to find its common ratio. Solution to this very problem. So we now have the sum to infinity and we have the first term of the GP. And what we are interested in finding here is the common ratio. So what we now do, I'll now write the formula. Sum to infinity, S infinity equals to A over 1 minus R. So there from the question, I now have my A first term, which is 81 in the question. Look at it. And the sum to infinity is also given in the question, 729 over 8. So I'll now substitute this. After substituting it to enable me to get this R, the common ratio. So substituting correctly, you now have 729 all over 8 instead S infinity equals to A. You now have 81 instead over 1 minus R. So I'll now cross multiply. There I'm going to have a 729 into 1 minus R equals to 81 times 8. So I'll now expand this very bracket. 729 times 1 gives you 729, and 729 times minus R gives you minus 729R equals to 8 times 81 gives you 648. So we now collect like terms. Collected like terms, 729R shifted to the right and 648 shifted to the left. That gives you 729 minus 648 equals to 729R. So subtracting 648 from 729 gives the result 81. So you have 81 equal to 729R. So next we now do is to divide both sides by the coefficient of R, which is 729. Dividing 81 by 729 gives a result 1 over 9, and dividing 729R by 729 gives you R. So R is now equals to 1 over 9. So with this, I have come to the end of this very lesson, my dear student. I hope you find it resourceful. Let me just move quickly to the last segment of the lesson, which is fun, and give you the relationship between twin prime numbers and the number 8. So let me first explain what are twin prime numbers. Twin prime numbers are consecutive prime numbers whose difference is just 2 only. Just 2 only. That is the difference between the first prime number and the next one. In the sequence of prime numbers, it's just 2. Let's just have some examples of twin primes. 5 and 7 are twins. 11 and 13 are twins. 17 and 19 are twins. 101 and 103 are twins. If you check the difference between 5 and 7 is 2, 11 and 13 is 2, 17 and 19 is 2. These are what we call the twin prime numbers. They are all prime numbers. They are in the sequence of prime numbers, but what happened, the difference between those two consecutive prime numbers is just 2. These are the numbers we call the twin primes. And these twin primes numbers has an interesting property or interesting relationship with the number 8. Let's just see. It says the sum of those digits in the products of twin primes. That means if we multiply any two twin prime numbers, the result, if you add those digits in the result, what you're going to have is this number 8. And this happens to most to most twin prime numbers. Let's just sample some. So if I take 5 and 7, they are twins. If I multiply it, it gives me 35. If I add 3 and 5, it will give me 8. Let me take another twin prime. 11 and 13 is twin primes. If I multiply, it gives me 143. If I add 1, 4, and 3, it will give me 80. You see, let me take one more. It's 617 and 619. These are twin primes numbers. If I now multiply, this gives me 381,923. And if I add this result, if I add the digits in the result, of course, it's bigger than 8. But if I continue, look at the addition gives me 26. But this 26, if I further add those digits in 26, look at it, it gives me 2 plus 6, it will give me 8. So even if the sum of the digits exceed 8, those number there, if you continue adding digits, surely it will take you to this number 8. And this happens to most of those twins prime numbers. This is really interesting. We see more of these things in mathematics in our subsequent lessons.